Alex already talked about the importance of shear in connection with large-scale dynamo action as opposed to small-scale dynamo action. That was the main focus of Alex's paper talk. In this talk, I will focus on the aspects of generating large-scale magnetic fields whose scale is larger than the scale of the eddies. And I will also focus on MRI disks in particular. So here's, first of all, shown a simulation without stratification at 512 cubed. It's a relatively short calculation. It's only 2 orbits. But we see a lot of eddies, many, many eddies in the meridional plane, elongated in the toroidal direction.
What field are you starting?
It's a random field. In this particular simulation, it was a remeshed from a 256 cubed calculation. And that, again, was a remeshed result from a 128 calculation. And that one, again, started with a sinus x times sinus y initial magnetic field.
I'm afraid that's...
So the initial magnetic field at a 128 cubed calculation, where one is able to have very long run times.
Zero mean field.
Zero mean field.
Okay.
The question now is, why don't we see any large-scale magnetic fields? Because Geoffroy Lesur yesterday showed us interesting results where one does actually see large-scale patches of magnetic field at certain times. One possibility is that maybe the run is clearly far too short, or maybe also the lack of stratification, which was what I was thinking in the olden days. Before I come to that, let me show a few other aspects of this particular simulation. Here is shown the vorticity. It's even more smaller scale, but in particular with reference to the poster of Toby Heinemann, here is the density waves in this particular simulation, where Toby has an interesting theory on the excitation of these waves. We yesterday saw some hand-waving arguments, or hand-waving demonstrations of how these density waves really look like, so that's how they look like in the simulation. Clearly in these simulations, there's no large-scale magnetic field. The energy is actually dominated by the small-scale energy. So the spectral slope seems to increase up to wave number 10. So this is quite different from any of the simulations of force turbulence that we have seen so far. Well, of course, one of the major differences is that here we have no control over the actual forcing scale. This may quite well be that the actual forcing scale is really at small scales here. Here we see the same thing as in an animated fashion. This kinetic energy, this magnetic energy. Yes, magnetic energy dominates at small scales, but there is no evidence of large-scale magnetic fields here. In this case, everything is periodic or shearing periodic in the x direction, yes. No stratification.
So essentially, when you do this, you conserve the flux boundary, right?
Yes.
You can possibly consider that k equals...
There's zero flux, therefore, yeah, in all directions.
So is it possible that the reasons you are seeing at small scales are because of, that constraints
at some level, yes, but in principle, it's still possible to generate magnetic field, of course, at wave number 1. The reason why you don't see this here can be manifold. There could be a connection with magnetic helicity conservation, of course. Sorry, what? Yes, yes. So it would be minus 5/3 for a Kolmogorov spectrum. In shell integrated spectra, the usual way. Per linear K, yes. Yeah. In that one, it was a fully explicit viscosity, yes, for the first time.
So what was the transfer number?
It was 1. And the Reynolds number, I forget what the value now was, but this is also difficult to define, of course. I mean, we have the viscosity, and of course we have, but Reynolds numbers are defined normally with respect to the RMS velocity. And the RMS velocity is fluctuating in time. That's what I meant. Can only be measured as posteriori. So let me now come to the connection with stratification. These were the old results of 1995, where the disk was stratified about the midplane, z equals 0, And over the course of the calculation, over 100 orbits, one saw the generation of a magnetic field that changed in its polarity in the midplane, and it changed polarity at a later time away from the midplane in about approximately symmetric fashion. Now, this was a result that has been repeated with that particular code over the following years. In particular, it was seen that the result depended quite significantly on the boundary conditions. If you go, for example, to a boundary condition which was no longer a vertical field condition, as this one is, but you go to a perfect conductor boundary condition, the result changed. And you obtained still a large-scale magnetic field in this simulation, but the parity was odd as opposed to even in this case. There are some tentative explanations in terms of mean field theory which seem to fit for this particular case. That is shown over here, where the critical eigenvalues are shown for different modes for an alpha omega dynamo in the appropriate conditions. Here we see that the first mode that goes unstable is an oscillatory even mode, whereas if you change the boundary condition, the first mode that goes unstable is an antisymmetric stationary mode, non-oscillatory mode. So this is a remarkable or interesting coincidence, perhaps. Since these results have not been repeated with other codes in the following years, I went back just recently and calculated the same thing with the pencil code that was not what was developed only afterwards. Here in this case, we have a tall box where the aspect ratio in the horizontal plane is 1:1, but then it's 4 times bigger in the vertical direction. Here clearly you see the generation of a large-scale magnetic field. It looks as if the parity here is odd about the midplane at this particular time, but things do change over later times. In this case also, the boundary condition is no longer a vertical field condition, but it's a potential field condition, which is more realistic in some ways. Both allow the outflux of helicity, but it's only the potential field boundary condition that also allows the outflux of Poynting flux. Tentatively, one can think that the importance of such open boundary conditions is that it allows you to produce net flux by the escape of a closed flux loop. If you have a closed flux loop, integrating over this would, of course, give zero flux. But if this leaves the box halfway through, there is a remaining flux left in one part of the domain. So here we have seen now several reversals over time. The magnetic field is not constantly fixed to the boundary. It does disappear, and it's being replenished by new magnetic field that comes. There's vacuum outside. That's what potential field condition means. So that means we are actually solving all the way to infinity, but with a current-free magnetic field. The movie goes much longer, and I don't have time to show all the rest of this, of course.
There's this inward group velocity.
Yes. Yes, that has a simple explanation. If I come back to this, I had here such a...
There shouldn't be any preferred direction in radio.
It's an optical illusion, which, let me see here. Here's go. So you have structures which move in this direction and back in this direction as time goes on, but these structures are inclined. So because these structures are inclined, it appears, if these structures move through the plane, it appears as if they propagate to the left.
Why is there a preferred direction to the inclination?
Here's zero shear velocity. Here is backward shear velocity. Here's forward shear velocity. So the structures are inclined. So if you have an inclined structure which moves through this plane, it of course appears like a translational motion. So as a function of time and space, these results can be shown as a ZT diagram. And we see again these similar structures as before. However, the parity is not always symmetric. Here it appears symmetric, but at other times, here it's again symmetric. But there are also times when it's more antisymmetric. So the parity is no longer strongly coupled to each other. Also note that the magnetic field really becomes well-defined only away from the boundaries, away from the midplane and closer to the boundaries. During longer simulations, this pattern is simply repeated. But if you do bigger boxes, the result is as yet unclear. So here is shown a bigger simulation, but it's also not run for quite as long. And it appears as if these structures are not so well defined anymore. But this, as I said, needs to be done. It's the mean toroidal magnetic field. So by mean, I mean it's averaged over the x and y directions.
How about the surface, the top, the first, and the bottom? Are they even parity or odd parity? Yeah, this is cut, so the z. But on the top surface is the bottom surface.
This is the bottom.
Right, but if
And
you
this
on the surface,
Yes.
top surface, the bottom surface,
Yes.
are they even or odd?
I don't understand this. What do you mean?
Yeah, yeah.
There is no parity about you in the xy plane. You mean?
The top, one surface is this, and the other is this. Are they similar pattern or opposite sides?
I think. Are you asking whether this is the same as here, and that you
If
do?
you have two-dimensional view, top, two-dimensional bottom.
I don't know. I mean, maybe I don't quite understand this question. Let's come back to this.
These are stratified?
Stratified, yeah. All of them are stratified. Already back in those days, when we saw these waves propagating outwards, we were interested in a possible explanation for this. And one possible explanation was always offered in terms of mean field theory. That, however, and we have seen this equation before, does of course require that we have some idea about what are the relevant coefficients for the electromotive force, U cross B, in terms of the mean magnetic field and the mean current. So these coefficients are called transport coefficients, which is part of the topic of this conference here. This is an alpha tensor. This is a viscosity, magnetic resistivity tensor. These can be calculated. There's a number of different methods. I will focus mostly on the so-called test field method, which I will briefly explain how that works. You have the original equation, induction equation. You can then average this equation. And by averaging, we mean here x and y averages. And that means that the averaged fields are dependent on z and t still. So these are one-dimensional averages. Subtracting this equation from that equation gives the residual, which we call the fluctuations. And this equation is well known in dynamo theory and is important to solve this equation. However, in order to calculate the electromotive force, we can now replace the averaged magnetic fields, which would, in a regular calculation, be coming from by solving this equation or by averaging the actual magnetic field. We replace this magnetic field by a so-called test magnetic field, and there are a number of different magnetic fields that are cataloged by indices P and Q. And then the corresponding responses to these test fields are called A, P, and Q for the vector potential. This method then gives rise to an electromotive force. For each test field, we have an electromotive force, which can then be expressed again in terms of the actual magnetic field. The first test field has a cosine, the second has a sine in the x component, giving rise to two equations for two unknowns. The unknowns are alpha 1, 1 at this point and alpha eta 1, 1, 3. It's a 3 in this tensor here. Two unknowns with two equations can be solved, and this is the result. It's a simple rotation matrix, and the same can be repeated for all the other components. This method has been validated using simple flow patterns. It's the so-called Roberts flow, for which the results are analytically known or semi-analytically known, both for the second-order correlation approximation, which we are not really interested in, but also for the non-second-order correlation approximation case, which means, which is the case when you don't neglect these quadratic terms or these nonlinear terms. So the results do agree with theory for isotropic homogeneous turbulence without back reaction. In the kinematic case, we find in particular that alpha is approximately, that's for fully helical turbulence, that alpha is approximately minus, because the helicity is positive in this case, it's minus 1/3 times the RMS velocity once the Reynolds number is larger than 1. For small Reynolds numbers, alpha is smaller, but once the magnetic Reynolds number achieves unity, the kinematic alpha reaches this value. the turbulent magnetic diffusivity quite accurately also reaches 1/3 times the RMS magnetic field, RMS velocity, multiplied by a length scale, or rather the inverse forcing wave number. So this is a dramatic agreement with the simple theory.
With MRI now, right? This is driven turbulence.
Yes, that's not MRI. And now I come to MRI, back to MRI again. So this was just for validation of this method and reference to previous papers, all of 2008. Now application to full MRI. And we see here the important component of the alpha tensor, which is a YY component, amplifying from a toroidal magnetic field, a poloidal magnetic field. The alpha effect is negative for positive Z's, except very close to the surface again. It's negative in here. That confirms earlier results already back in 95. The other components also known. These two antisymmetric off-diagonal components are referred to as pumping effects. We also have now, for the first time, full access to the viscosity tensor, resistivity tensor, and we see that the resistivity is large away from the midplane. Both are equally big, approximately, which we have not seen so far in much more simplified ways of calculating this with the correlation method. And in particular, we see that the off-diagonal component Yx, which has some particular significance, as I will explain in the next view graph, is positive. So why is this component potentially important? That's because there is a possibility of a so-called shear current effect, which has been argued to explain a mean electromotive force in the presence of a mean current alone and without any alpha effect. So there is this theoretical possibility if this eta to 1 component or Yx component has a right sign. As one can see here, if the shear, of course, in accretion disk is negative, and if this term is also negative, then this gives a positive contribution to the growth rate, a non-imaginary contribution positive to the growth rate, and could lead to dynamo action. But as we have seen in the previous view graph, this sign is positive, and so with negative shear, this cannot lead to a shear current effect. Going again away from MRI disk and to the case of purely shearing domain, here in this case with periodic boundary conditions, so no MRI, no rotation that is, but with shear, we see that there is still the possibility of generating large-scale magnetic fields or large-scale patches because these have the length scale over the domain of the box, the size of the box, but they do show reversals on the time scale of several eddy turnover times. So there is the similarity with pictures that we have seen yesterday by Geoffroy-Lesur, and the question is, how can those magnetic fields then be explained if it's not the shear current effect, and since there's also no alpha effect? In those particular simulations, again, we have verified that the shear current effect, that is the eta 2-1 component, is positive throughout. There's perhaps a possibility that it may change sign at larger RMs, but there the error bars also become much larger. Another possibility that I've mentioned already yesterday in the discussion is that these fluctuations in the alpha tensor, which fluctuate clearly about 0, any of the 4 components of alpha are plotted here, they show a Gaussian distribution about 0. But the excursions are occasionally very large, and it's a question whether this could explain magnetic fields through what is known as the incoherent alpha shear dynamo. Such cases have been investigated by Ethan Wishniak and myself since 97. And here's a simple model calculation where we simply calculate the usual alpha omega dynamo equations, but with an alpha effect that is fluctuating in time and in space. And so here's shown the result, how that would look like. So tentatively, we think that could explain this. Those dynamos have clearly a marginal excitation rate. If marginal excitation condition, if the dynamo number based on this RMS alpha effect is larger than a certain value, those are excited. So with these possibilities, let me conclude then that first of all, cycles have been seen again now in simulations with stratification. There is, of course, a possibility that it may depend on the proximity of the boundaries, which needs to be established. But on the other hand, also these runs all need to be carried out for long times, which has not been done in all cases. In some cases, some connection with mean field theory can tentatively be established by measuring the alpha and eta tensors. However, although an alpha effect can explain the magnetic field in the stratified disks, we think that there's no explanation in terms of the shear current effect for unstratified disks, and the only possibility in those cases is then that it could be an incoherent alpha shear dynamo effect. Thank you.
Could you comment on the boundary condition at top and bottom? Is the velocity zero?
Yes. It's a stress-free condition for the velocity field here, yes. Is this what's periodic? Yes.
Do you have to put in a force to do that, or is it just automatic?
Force, did you say?
Well, I mean, you would normally expect some overturn.
The velocity is... It's a boundary condition for the velocity field, and the boundary condition for the magnetic field can be expressed as well in terms of a non-local boundary condition, which is standard, of course. Yeah.
You have an electric field directly proportional to a magnetic field, which is what the alpha tensor does. The alpha tensor
On the average.
must not be an ordinary scalar, but a pseudoscalar.
Yes, correct.
So, which means that you have some kind of handedness
Yes.
in the bottom.
Yes.
What is responsible for that?
It's the stratification together with the Coriolis force. That gives you a handedness like the cyclones in the northern and southern hemisphere of the Earth.
Yeah, because what I'm trying to look at the picture, looking down the disk, up the disk, I mean, not
Yeah.
the cross-section, but do you see the pattern, the handedness?
It's very difficult to see visualize such a thing. Yeah, it's
Well,
difficult.
you take snapshots, you know, looking
Yeah,
looking
it's
down, looking up the disk.
as you know, if you look at a mass, it's difficult to make out any regular patterns, of course.
We have a pattern here, you know, it's a green, you know,
But this is an average. This is not the
average
over x and y.
over
Over x and y. Yeah, horizontal planes.
So you think that this sort of butterfly pattern, or whatever you
Yes.
call it, is a consequence of the dynamo equation,
Uh-huh.
in which case it should be more or less independent of the strength of the field. And this is an average, as you just said. Another thing that could cause rising like this is just buoyancy.
Yeah.
Have you, if you instead of just taking an average of whole things, have you checked to see whether there's any correlation in the rate of rise with the strength of the field?
First of all, I agree this is tentatively possible to explain this in terms of buoyancy, but there has been no such calculation yet, or so no such model. But what do you mean by, what did you say?
Well, you could divide each
but is
horizontal plane into strong field regions and less
Yes.
weaker field
Why should the magnetic field strengths be critical here?
Well, if it's
Yes,
buoyancy,
of course.
field strength matters.
Yes, yes. I mean, for buoyancy, is there maybe there could of course be the problem that the box is rather narrow, right? And for Parker instability, you need very long boxes in the toroidal direction, which is not the case here. Just buoyancy as such, yeah, no Parker. Okay, perhaps. But whether, yeah. Toroidal flux is not conserved in those calculations, no, because there's a potential field condition.
Yeah, so I was wondering whether the toroidal flux that comes in Berlin is significant. And whether it can
It's significant in its strength, yes. It's large amplitude, of course, yeah.
it varies with time.
It varies with time, as you see here. Why?
Is there a
Mhm.
Is there a turbulent
Turbulent eddy. I mean, oh, yes, there is, what we actually do have is so-called shock diffusion. That's the only thing that is included. There's no hyperdiffusion, but shock diffusion is included. And in those outer layers, there is a possibility of shocks. And so that would increase. Mixing?
You add that resistivity
Yes.
to determine the shocks.
Yes, and that is added on. But it's only added on for the viscosity, not for the magnetic field. So the resistivity is actually independent of this shock diffusion. So the eddy diffusion is a completely irregular Spitzer resistivity throughout, and it's constant in this calculation. Unlike yes, it's just Spitzer. No eddy resistivity. No, not for the resistivity. Only for the viscosity. It's eta, yeah. It's completely constant.
Maybe